Hi, this is Math 2231, remote delivery for April 30th, 2020. This is part 2, and we're scratching the surface of hyperbolic trig functions, and when you see this, you know what to do and when to do it. The catenary is a plane curve, and shape corresponds to a hanging, homogeneous, flexible chain supported at its end and sagging under the force of gravity. Thomas Jefferson actually came up with this name, our third president. It's very important from an engineering standpoint because the Gateway Arch and other structures in architecture and construction use this because it has wonderful engineering properties, and there also are some good physics properties of this too. It is very important in applied math. If you study the engineering associated with it, you end up with an expression that differential equation actually that looks like this. And it is kind of a nasty differential equation because you see you're taking t0 as a constant, and this is going to be, you're taking the derivative of y prime, which means it's y double prime, and here you have y prime squared, so it is nonlinear. So this is a second order differential equation. It's nonlinear and it's a little bit nasty, except if you say, oh, I will make a substitution of z equal y prime, then what will happen is this second derivative becomes just z prime, and y prime squared becomes z squared. Now this is something that's very familiar from the earlier lecture today. This is a separable differential equation, so we can separate the variables. So we will get the z's on one side and the x's on the other, and that means all we have to do is integrate, if we can integrate this expression. Now, you might not know how to do that. In fact, you probably don't know how to do that, but it is a good question for me to ask is, can you show that this in fact is true? And I'm not going to take your time having you try to do this, but you should be able to do this. We've done this several times. If you take the derivative of this side, you should be able to get the integrand, 1 over the square root of 1 plus z squared. I encourage you to try that on your own time. But anyway, now we know what that integral is. Let's go back to, here we had separated variables, so now we integrate this side. We know that this is this, and when you integrate dx, you get x, and we're going to call this constant 1 over a, and then we have plus c1. So we've just integrated both sides, and again we called that constant 1 over a1. Now, if we talk about the tangent to the catenary at its lowest point, well, that's going to be flat there, so it's parallel to the x-axis. So we know that z evaluated at x equals 0 is the same thing as y prime evaluated at x equals 0 is 0, which means that we can substitute those values up here. Now the natural logarithm of 1 is 0, so we can conclude that c1 up here is 0. So what we have is c1 is 0. That means that, and this is the natural logarithm, that means logarithm base e of this stuff is this. So that means, as when we talked about logarithms, that the expression here is e raised to the x over a. Okay, we're going to use that. Again, we're going to use that. Now, if we multiply both sides by the conjugate, z minus the square root of 1 minus z squared, here we're going to get z squared minus 1 plus z squared. The z squareds will cancel, so I will get minus 1 is equal to, here's the conjugate times that. So if I solve this, then I find that z minus the square root of 1 plus z squared is minus e to the minus x over a. Well, you see I combine this one and this one. If I add them, I will get 2z. The square root of 1 plus z squared will drop out, and I will be able to say that z, which is the same thing as y prime, is e to the ax minus e to the minus ax all over 2. And think about this as we go forward in a bit. We're going to call that the hyperbolic sine. But now you see we know z was y prime, so we have to integrate that. Again, you should be able to integrate that. I'm not going to have you do it right now, but if you integrate that, you should get that y is a, and then this is e to the ax plus e to the minus ax over 2. Now it turns out these last two functions that we talked about, and you saw how they came up naturally in the applied math problem, are known as the hyperbolic sine and hyperbolic cosine. They're very useful in applied mathematics, and whereas the sine and cosine are associated with the unit circle, these functions are associated with hyperbolas. You'll see that there's some similarities, but also there's some striking differences. Let's review some of these. Well, so here's the definition of the hyperbolic sine, and that's pronounced sinh. And this is the hyperbolic cosine, and that's pronounced cosh. And from these, you can define a whole bunch of other hyperbolic trig functions. The tangent would be the sinh divided by the cosh. The hyperbolic cotangent would be the cosh divided by the sinh. The secant is the reciprocal of the hyperbolic cosine, and the cosecant is the reciprocal of the hyperbolic sine. So these are important graphs, again, in applied math. We also have identities, but notice that the identities are sort of similar, but sort of different. For example, instead of the sine squared plus the cosine squared adding up to 1, here we have that the cosh squared minus the sin squared is equal to 1. Whereas before, we had, when we were talking about derivatives, the derivative of the cosine was minus sine. Here it's just the sinh. Some of the SIG and S's are different. And every time you have a derivative formula, you have an integral formula. So there's quite a bit of things here. And those functions, if you restrict the domain, those functions are one-to-one, meaning that they have inverses. And these are some important integral formulas that you will run across significantly in applied math. And you see, you can evaluate these using the inverse hyperbolic functions. So what? Well, these are in the official Calculus 1 curriculum documents today. But I also can tell you that they're in the process of being moved to Calculus 2. Other things are being moved into Calculus 1. Things are being moved around a little bit. I've taught Calculus 1 many times, and covering them at the end of the Calculus 1 has made some strongmen and women cry. Often they're fatigued even without COVID-19. And then later, when I introduce them in a differential equations context, most students claim never to have seen them. So, the hyperbolic trigonometric functions will not be a part of your final exam or the upcoming quiz over post-Chapter 4 material. But we did cover them, even in the era of COVID-19. The balance of the term next week will be spent reviewing for the final. Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other.